Starting with a very brief introduction of the speaker, and it's a great pleasure to introduce Sourav Chatterjee from Stanford University. Sourav is a professor of statistics and mathematics, and he's known for his remarkable contributions in a really broad range of topics covering statistics, probability theory, and mathematical physics. He's essentially won all awards that there are in probability theory. And in this seminar, we're particularly happy about his interest in gauge theory, on which he will report in this talk.
Okay. So should I start?
Yeah, please.
I think so. I think as more or less the number of participants has more or less settled, I think.
Okay, so thanks a lot, Roland, for the very kind introduction, and thanks to Roland and the other organizers for inviting me. So it's very nice to see to see everyone in little windows. So, but still, it's nice to see a lot of people I know. Okay, so I'll start with a general introduction, and I suppose many of you in this audience are familiar with all the introductory material that I'm going to present, but I'll still define things and talk as if there are people in the audience who do not know what this is. So let me start with the Yang-Mills action, and I'll skip the motivation because there is a lot of things that I have to say. So let G be a compact Lie group containing the unitary group of some order, and let this Gothic G be its Lie algebra, and let A be the script A be the space of smooth G connections on the trivial principal bundle. So if you don't know these terms, don't worry. It's just a set of all smooth functions from the Euclidean space R to the D into D tuples of Lie algebra elements. Okay, so this is the space script A, and the curvature form of a connection is defined as this D by D array, where fjk is del ak del xj minus del aj del xk plus the commutator of aj and ak at a point x. So at each point x, you have a D by D array of elements of the Lie algebra. Okay, so that's the curvature form. And the Yang-Mills action is defined as minus the integral over Euclidean space, the sum over all j and k trace of fjk squared. So remember, these are matrices because G is a subgroup of UN. So the A's are n by n matrices, and provided that the integral is well defined. So this is the Yang-Mills action of a connection. And these are the basic objects that we study in these gauge theories. Okay. So what are Euclidean Yang-Mills theories? Heuristically, Euclidean Yang-Mills theory on R to the D is a probability measure on the space of connections with a density proportional to e to the minus beta the Yang-Mills action with respect to some hypothetical Lebesgue measure on the space of connections. And beta is a coupling parameter. And this hypothetical object is sometimes called the Yang-Mills measure. And the construction of this measure in 4 dimensions is a key step to the solution of the Yang-Mills existence problem, which is still open. So this is an extremely brief summary of the thing, and there's a lot more to say. Okay, so this is the thing, and then another important thing that we need to mention in this context is the concept of gauge transforms. So take any connection A and any differentiable map from R to the D into G, into the gauge group. And then you define a transformed version of A as follows. You take, at each point, you take Gx inverse AJX Gx. So A has D components, remember. So for each component, you do this, plus Gx inverse del G del Xj. So this is your new connection, and you can easily see that this whole thing is also an element of the Lie algebra. So you again have a D tuple of Lie algebra elements at each point. And this transformed field is called a gauge transform of A. And each choice of this G any differentiable map from G from RD into the group induces a gauge transform. As a fact that A is also gauge transform A to the G, so which is just gauge transforming A to the G by G inverse, you get back A, and these are, and so actually this action is a gauge is group action, and this is a group under pointwise multiplication, and these A and A to the G are called these are called gauge equivalent. Okay, this is an equivalence relation, and the space script A of G connections is not the physical relevant space, rather the quotient space A modulo G is so this script G is a set of gauge transforms. This is the physical relevant space. Okay, so for example, if you consider the gauge group U1, what you get is the electromagnetic field, and in that case, this space script A is again the space of gauge fields, but this quotient space is in one-to-one correspondence to the field of consisting of electric and magnetic fields. So there are three components of the electric field, three components of the magnetic field, and each element of this quotient space corresponds to one particular configuration of electric and magnetic fields over space and time. Okay, so this is the physical relevant space. Whatever the Yang-Mills measure is, we should define it on this quotient space. Now, so there's another concept called gauge invariance we should know. So function f on script A is called gauge invariant if f is the same on each equivalence class. So fa equals fa prime whenever a and a prime are gauge equivalent. And for example, it's not difficult to check that the Yang-Mills action SYM that I defined a couple of slides ago is gauge invariant. Okay. So and any physical observable must be gauge invariant. Okay, so that's the basic hypothesis, that anything that you can observe or deal with must be gauge invariant. And I'll talk about later, the most important gauge invariant observables are the Wilson loop observables. So these will be defined later. So sorry, I'm going very fast, just with the assumption in the back of my mind that people are all familiar with this. But if you are not, feel free to ask a question. And anytime, just unmute and ask. Yes. Hi.
Hi, yes, okay. Just a quick question. The gauge transformations, don't one usually say that these gauge transformations should be, are you including this large gauge transformation that at asymptotic values are not trivial in this gauge invariant? Because
okay, so I was not being very careful. So typically we will work on a torus, so that wouldn't matter so much. So let's yeah.
Okay.
Yeah. So this is just for presentations. I'll just work on a compact manifold. And so as I was going to say, anytime there's a question, just unmute and ask. And also, as in the title slide I mentioned, this is joint work with my student Sky Cao. And Sky is also present, so you can also just, if you have some technical thing, and you can just send a message to Sky also on the chat, and he'll be happy to answer. Either way is fine. So you can just unmute and ask me, and or send a question to Sky. Okay, so. Okay, so what's the progress so far? So one common theme in the literature is look at the problem in dimensions 2 and 3 instead of 4. And the greatest amount of progress has been made in 2D. And in fact, we now know how to construct the Yang-Mills measure in 2D. On the other hand, very few results are known in 3 and 4 dimensions. And many of the above results are for compact manifolds such as tori instead of the full space. And this is what we will work on the torus. So again, a very quick summary of the results. So many authors have made contributions to understanding 2D Yang-Mills theories, and in chronological ordering, these are some of the papers. Although it's an incomplete list, there are many other works. And in one of the very recent papers of Chevirev, there is a construction of a space of connections and a probability measure on this space of connections that can be interpreted as a 2D Yang-Mills measure. And to contrast, previous works constructed measures on spaces of observables instead of directly on the space of connections. So now we have perhaps the most direct construction of a 2D Yang-Mills measure. And also there is this work that came after of Chandra, Chevirev, Harer, and Shen. They construct a state space and a Markov process on the state space such that the unique invariant measure of this process can be interpreted as a 2D Yang-Mills measure. So it's not known whether the unique invariant measure exists as far as we know. So this is a very, very quick list of things that have been done for 2D Yang-Mills. But this talk is mostly about 3D Yang-Mills. So let me mention something about 3D. So in this paper of Chandra et al, they mentioned that they have some forthcoming results in 3D, but I don't know what those are. U1 theory is not difficult to construct in any dimension since the Yang-Mills measure is Gaussian. I mean, the continuum U1 theory is just a Gaussian theory. The problem becomes far more challenging for non-abelian theories. And the state of the art is, there were a lot of work in the 80s and early 90s on this phase cell renormalization for 3D. And so I'll come to that, what that means for a general non-abelian Lie group. However, it didn't seem to us that the Yang-Mills measure was actually constructed as it was done in the 2D case. So in 3D and 4D, we didn't see that. So that is again an extremely quick summary of what is known about this problem. So to understand the main difficulty in constructing Yang-Mills theories in dimensions 3 and higher, we have to first understand what's called a Wilson loop observable, which, as I said, is the main observable, or what probabilists would call the main class of measurable functions that we're interested in. And what's a massless Gaussian free field? So there is a reason why we need to know about that. So I'll introduce these things, and again with the assumption that that the audience is not familiar with it, but just stop me if I'm going too fast. Okay. So any questions so far? Okay, so I've not presented anything technical. Just the definition of, or I mean, the heuristic definition of what should be a Yang-Mills theory. Okay, so what is a G connection? So we have seen earlier that the Yang-Mills measure is supposed to be a probability measure on some space of G connections on a principal bundle where G is a compact Lie group. To fix ideas, let's say our principal bundle now is the torus. So let's restrict ourselves to a compact domain. So this trivial bundle T to the D cross G, where this is the D-dimensional unit torus. So one can think of this bundle as a copy of the group sitting at each point on the torus. Okay, and the main role of a G connection A, so that these connections that I demonstrated, that I displayed, the main role is to give a prescription for a change of coordinates. So suppose you have an element G at a point X, and as you move along a curve, how this element changes to some other element as you move along the curve. So it's a notion of parallel transport. So we say that G is parallel transported to H along a curve L. Okay, so this is what a connection does. And how do you define the parallel transport? Let A be a smooth G connection, so a connection on the torus. Let's say you have a piecewise C1, or just a smooth path on the torus, and then define phi to be the solution of this differential equation. So phi at each point in 0, 1, phi is a group element. So you start with the identity, and then you let it solve this equation. Phi prime of t is phi t times summation j equals 1 to d aj l t times l prime lj prime t, where these are all matrices. So these are all n by n matrices. So this result is also an n by n matrix. And from standard or differential equations theory, phi exists and is unique. And the group element phi 1 is a parallel transport of the identity element along the curve L. Okay. And when G is U1, so just specializing to U1, these are, each AJ is a function from T to the D into the imaginary axis. So the Lie algebra is just the imaginary axis. So the parallel transport is simply the exponential of this line integral. So this tells you, this equation tells you, so in this case, these are all imaginary numbers just. And so then this is just the exponential of this line integral, okay, along summation aj dxj along this line L. And when G is non-abelian, these are non-abelian matrix valued functions. So it's not exactly the exponential of this integral, but it's what's called the path-ordered exponential of the line integral. Okay, so it's still a line integral, exponential of a line integral. It's just not the ordinary exponential. It's a path-ordered exponential. Defined as a solution of this. So it can be, the path-ordered exponential can be defined as follows: solution of this differential equation. Okay, so this is parallel transport. So the next thing is observables. Any physical theory should have observables. That's a function of a state space. Function of a state space whose values can be the result of experimental measurements. For gauge theories, the parallel transports defined by these connections are natural observables. Okay, so you have this connections, and then you have the parallel transport, which is the job of a connection, how to do the parallel transport, and these should be natural observables. But the problem is that they're not gauge invariant, and so therefore they're unphysical. And even if you, instead of a line, you take a loop, the parallel transport is still not gauge invariant, but it is gauge covariant, meaning that if you take the gauge transform of a connection by a group element, by a gauge transform G, you do the parallel transport, you get G inverse the original parallel transport times G. So you get this gauge covariance. And so if you apply a character to this, okay, so if you take the parallel transport along a loop and then you apply a character of G, then this G inverse and G, they don't matter because it's a class function. So you just get that this is a gauge invariant observable. Okay, so this becomes gauge invariant. And these are called Wilson loop observables. Okay, so you have this connection, you take parallel transport along a loop, and then you apply a character to that. And this is called the Wilson loop observables. These are the basic observables in gauge theories. And they are also important for many physical purposes. So they arise in the problems of quark confinement and mass gap and a lot of other things. So these are the fundamental observables of a gauge theory. Okay, any questions so far? Okay.
Sorry.
Yeah.
A question. So what's the definition of a character?
Okay, so character is you take a representation, finite dimensional. So I'm just considering finite dimensional representation. So finite dimensional representation. I mean, these are compact groups anyway. So you have a finite dimensional representation and take the trace of that. So that's the character.
Okay.
Yeah.
Thanks.
Yeah. So you can see as soon as you take a representation, this G inverse and G. Well, then you have to take the trace of that. So you can.
Yes. Okay. Thank you.
Sure.
Sourav?
Yes. Hi.
Hi. Is there a reason for allowing complex observables? Like, why not take the real part of a character instead of a character?
Yeah, you can do that. Yeah, you can do that. I mean, that's what I think is usually done. But we are keeping it this way. It doesn't. For our analysis, it doesn't matter so much. Yeah, so usually the real part is taken. You're right.
Sorry, can I ask a question?
Yeah.
This is classical observables,
Uh-huh.
right? It's a classical theory with a classical observables.
Yeah.
As a functions on the phase space of the theory.
Yeah.
Is it right?
Yeah.
Okay.
Yeah. These are classical observables. Yeah. So we are doing Euclidean field theories. So we haven't yet gone to the quantum theory. So the thing about these Yang-Mills, quantum Yang-Mills theories is that there is this program of constructive field theory, which if we can construct these Euclidean field theories, which are basically should be statistical mechanical objects, then you can use those and then use the Osterwalder-Schroeder actions to get a quantum theory out of that.
Okay.
But let's start with these statistical theories.
Okay,
Yeah.
thank you.
Yeah, sure. Okay, so the next thing that we briefly have to introduce is the massless Gaussian free field on the torus for D2 or higher is a random distribution with the property that for any two smooth functions f and g on the torus, phi f and phi g, are jointly Gaussian random variables with mean 0 and covariance given by integral fxgy times gxy, capital Gxy, where g is a Green's function on the torus. Okay, so that's a Gaussian field. It's a random distribution, and when you apply the random distribution to some smooth functions of the torus, you get real numbers, and they are jointly Gaussian random variables with mean 0 and this covariance. So this is a Gaussian field. And you can, hypothetically take this f and g approaching delta functions at 2 points x and y. And if you put that, you get the covariance of phi x and phi y is gxy, which if x and y are distinct is a finite number actually, although phi is not defined pointwise, you can have its 2-point correlations being finite pointwise. And the covariance blows up as y tends to x, and this is consistent with the fact that phi is infinity at any given point. Okay, so here is some heuristics. It's not mathematically justified, but so recall that Euclidean Yang-Mills theory is supposed to describe random G connections on principal bundles, let's say the trivial bundle. And it's believed that these random connections are not really random functions, but rather random distributions, whatever that means in this context. These are random distributions. And furthermore, it is believed that component-wise, these random distributions have similar behavior as the massless Gaussian free field. So on local scales, there is similarity with the free field. So it has the same amount of regularity as a free field and other things. And this is actually rigorously known for 2D theories, for example, in the recent work of Chatterjee that I mentioned, but not in higher dimensions. So in 2 dimensions where people can actually construct 2D Yang-Mills theories as random distributions, you can show that these random distributions that come up are, at some level, they are like the free field, on small scales, they're like the free field. Because that's why we need to know what's the free field. Okay, so now the main difficulty about these Yang-Mills theories. So assuming that Yang-Mills theories behave like massless free fields, let's consider the question of computing Wilson loop observables. Okay, so recall that the Wilson loop observables are defined using line integrals. So let L be a loop, and suppose we want to integrate a massless free field along a loop. The Green's function blows up like log 1 over x minus y as y approaches x when d is 2, and like the x minus y to the 2 minus d when d is 3 or higher. So they blow up much faster when d is 3 or higher, and they blow up kind of slowly if d is 2. So from this, one can show that the line integral of the massless free field, although it's a distribution, its line integral along a suitable curve in a smooth loop is well defined in 2 dimensions. You can show that, but it blows up in higher dimensions. So you just formally write down the line integral and try to compute its variance. So when you compute its variance, it becomes a double integral of covariances of phi x and phi y along the loop. And this double integral is finite when d is 2, but as soon as d is 3 or higher, you will see that it blows up. So we do not expect to be able to define Wilson loop observables directly in d3 or higher. So in 2 dimensions, you can, although the field is extremely rough, you can define Wilson loop observables along loops. But in 3 or higher, you do not expect to be able to define Wilson loop observables. So some indirect approach has to be taken. Okay. Any questions about this slide? Okay. So what we do is renormalization, or just you can say regularization. So since Wilson loop observables are unlikely to be definable for Euclidean Yang-Mills theories in dimensions 3 and higher, one idea is that we should first make the theory smooth by some kind of regularization. Okay. The problem is that the regularization needs to be gauge covariant, meaning that if you take a connection and you regularize it to make it smooth, and you take a gauge transform of that connection and then you regularize, you should get the same gauge transform of the regularized version. Okay, so that this regularization is not really a regularization on the space of connections, but on the physical space, the quotient space. So it has to be a regularization on the quotient space. So you have an element of the quotient space, and that's what you're regularizing to get a more regular, smoother element of the quotient space. Okay, so that's one of the main difficulties, that you have to do this something complicated. It's not just some simple-minded, averaging that you can do. So a simple regularization such as taking convolution with a smooth kernel is not going to work. Okay. So the works on Yang-Mills in the 80s focused on lattice approximations of Yang-Mills theories. And the smoothing that was adopted was usually a complicated gauge covariant procedure known as phase-sale renormalization. And as far as we can tell, this program was not completed. The construction of the Yang-Mills measure via this approach was not completed. So this is the main problem, that you need to be able to do this, in a gauge invariant way, or gauge covariant way, this regularization, so that you are able to define Wilson loop observables or other observables on these regularized theories. Okay, so this is where our work begins. So the idea that has emerged in the last 15 years or so is that Yang-Mills theories can be regularized. You don't have to look at lattice approximations. You can directly look at continuum theories, whatever they are, by what's called the Yang-Mills heat flow, which is a gradient flow of the Yang-Mills action. So we'll define this soon. The Yang-Mills heat flow has a long history in math and played an important role in the work of Donaldson and others. It started with the paper of Atiyah and Bott. So it had a long history. The idea of renormalization by the Yang-Mills heat flow appeared, as far as I can tell, in the works of physicists, these two papers, early papers on this, on the Yang-Mills heat flow, using, regularizing Yang-Mills theories using the Yang-Mills heat flow. The advantage of the Yang-Mills heat flow over the ordinary heat flow is that it's gauge covariant. So it has this property that it's actually a smoothing operator on the quotient space. So if you take a connection, you take a gauge transform, and then you regularize, you get the same gauge transform of the original regularization that you have, starting with the original connection. Okay. So this becomes a legitimate smoothing apparatus for Yang-Mills theories. Okay, so what's the Yang-Mills heat flow? So given a G connection A on the torus, recall the curvature form. This is how it was defined. And the Yang-Mills heat equation is the following nonlinear PDE that describes the evolution of a time-varying connection AT. So A, remember, as D components. So each component evolves as follows. Del AJ del T is minus del FJK del XK, K equals 1 to D, minus K equals 1 to D, AK FJK. So you see, this is a sort of a cubic term because the commutator appears here. So you have this whole FJK here. And this term also has some nonlinearity. So this is quite a nonlinear equation. And it's just the gradient flow of the Yang-Mills action. So it's basically taking this connection, looking at its Yang-Mills action, and just trying to flow in the direction which decreases the Yang-Mills action most sharply. Okay, so that's it's the steepest descent for the Yang-Mills action. Okay, so the Yang-Mills action, from the definition, I didn't mention that. You can see that it's always non-negative. And then you want to make it smaller and smaller, and so this is the variational problem. If you solve the variational problem, you get this equation out of that. Okay, so that's the Yang-Mills heat flow. Now, what people often work with is a variant of the Yang-Mills heat flow. So I'll tell you why it's equivalent. So people work with a variant of the Yang-Mills heat flow discovered by these authors, Wanziger, De Turk, Donaldson, Sadoun. So this is this flow. So del T AI is the Laplacian of AI plus this whole nonlinear term. And with so let's call the ZDDS flow in honor of these authors. And it's related to the Yang-Mills heat flow as follows. So if CT solves this equation and AT solves the Yang-Mills heat equation, the same initial data, you can show that CT is a time-varying gauge transform of AT. Okay, so it's CT is always a gauge transform of ET, but the transform itself is changing over time. And so what this implies that if you take these flows on the quotient space, they're exactly the same flows. So they're just the same flows on the quotient space. They may be different flows, completely different flows on the space of connections, but on the quotient space, they are the same. Okay. And for this reason, this flow is sometimes called the Yang-Mills heat flow in the De Turk gauge. Okay, so in a different gauge. It's the same equation in a different gauge. And there is a standard way to derive, and physicists derive it as gauge transform. So this is how it's done. Okay, so recall that Yang-Mills theories are believed to be random distributions with similar features as a massless Gaussian free field. So for the renormalization using Yang-Mills heat flow to be a valid procedure, yes, Malik.
Sorry, Sourav. The reason to use this alternate flow, is it because the linear part is elliptic, or is there more?
Yeah, no, this is much more convenient. So you have this term here, Laplacian, and so the mathematical analysis somehow becomes more convenient if you use this. Yeah. So recall that Yang-Mills theories are believed to be random distributions with similar features as a massless Gaussian free field. So for renormalization using the Yang-Mills heat flow to be a valid procedure, we need that the solutions to the Yang-Mills heat flow, or equivalently this other flow, should exist for initial data that behaves like a free field. Okay, that's the first thing one should know. So suppose you have something that is like a free field, a distribution. Can we have this flow? So that's not a meaningless question, because the ordinary heat flow, for instance, can start from distribution. So you can have distribution and it can be instantly regularized by the ordinary heat flow and become a smooth function as you apply the ordinary heat flow. So you start with the Dirac delta, for instance, instantly it becomes a function. So you can imagine that if you start with this very rough, free field like initial data, instantly it becomes a function as we apply this heat flow. But the nonlinearity of the PDE makes this a challenging problem. And the available results about the Yang-Mills heat flow do not allow initial data that's rougher than H1, which is basically, you should have derivatives, and the derivatives should have finite norms, so which is quite smooth. In particular, distributional data is not allowed. Okay, so here is the program initiated by Charalambous and Gross. So Len Gross and Nelia Charalambous in a series of, papers between 2010 and 17. Sorry, I'm feeling a little sniffly. Increase this allowed roughness to H12, okay, from H1 to H12. And the goal was to construct 3D Euclidean Yang-Mills theories as trajectories of the Yang-Mills heat flow. So you can view a distribution. So one of the main challenges is to construct distributions on the quotient space. So usually, how do you define distribution? Distributions are linear functionals on a vector space of functions, right? So that's a distribution. But when the quotient space A/G is not a vector space of functions, right? So it's a complicated nonlinear space. So how do you define distribution? So you can think of distributions in a slightly different way. So on Euclidean space, distributions can be seen as linear functionals on a space of functions, but they can also be seen as trajectories of a flow. So for example, trajectories of the heat flow. So suppose you have a heat flow, you have the ordinary heat flow on Euclidean space. Then starting from a distribution, you get a function. So let's say Dirac delta becomes a function. So if you look at the full trajectory of these functions that you get by applying the heat equation, starting with the distribution, if you get its full trajectory, excluding time 0, the trajectory is in one-to-one correspondence with the distribution itself. So distribution on Euclidean space can be seen as being in one-to-one correspondence with the trajectory of the ordinary heat flow. So similarly, the idea was to construct random distributions on this quotient space as trajectories of the Yang-Mills heat flow. Okay, so that was the idea. And this roughness was decreased to H12, but H12 is still a function space. It's not distribution. And the massless free field has regularity H minus half, a little less than H minus half minus epsilon. So how do you go there? And from these arguments, it seems possible that a general existence theorem cannot do better than H12 for initial data. So if you consider worst case as we do in PDE, that that you consider worst case initial data, you cannot have it better than h-half. So there may be some truth to that. So here is our main result. So we'll post it on archive. It's not yet on archive. It will be on archive very soon, maybe in a week or so. So it's possible to define this Yang-Mills heat flow in the deterred gauge on the 3D torus starting from free field initial data. And moreover, the initial data need not be exactly the free field. So we give a list of conditions. It suffices for it to be a random distribution having certain features of the free field. Okay, so you can actually do this. Okay. And then also there's another preprint that's coming up. So it's possible to construct a state space for Euclidean Yang-Mills theories on the 3D torus as a set of trajectories of the Yang-Mills heat flow and have a criterion for the existence of a convergent subsequence given a sequence for a given sequence of probability measures on the space, so an analog of Perhaps theorem. Okay. So these are the two main results that that we have in two separate preprints that we will post soon. Okay. And I'll give you some more details shortly. But any questions for now?
Is this a global or a local existence when you say?
It's local existence. Yeah, it's local existence. Yeah, it's local existence, although it is global in a sense because once you let it flow a little bit, it becomes a smooth function. And for the 3D torus, it's known that if you start with a smooth function, there is a global solution. So that's a classical result that for the Yang-Mills heat flow, and I suppose I don't know whether the result directly exists for the deterred gauge, but probably because deterred gauge is always easier. So there are global existing results. There's a famous result for Rade from 1992 that for the 3D torus there is a global solution. So in some sense, yeah, we have a global result in that trivial sense that we can prove local existence, but then after a finite amount of time, it instantly becomes smooth, and then you have global existence by existing results. Yeah.
So I believe in the approach by Chandra and those guys. They look at the stochastic flow where the invariant measure arises as some kind. Kind of like a Langevin equation in infinite dimension. But in what you're doing, the randomness is only on the initial condition, and afterwards the flow is purely deterministic. So,
yes.
So how does the measure arise then?
Oh, so we are not constructing the measure. So we're just saying that this so this equivalent of this phase cell renormalization. So this regularization can be done if you have the Yang-Mills measure, which is very rough, okay, which is supposed to be very as rough as the Gaussian free field. If you have that, then this is a valid renormalization procedure. So then you can you renormalize using the Yang-Mills heat flow, and you can express the resulting thing. So we are not constructing that, so that's why it's not a fully solved thing. So I'll tell you what's remaining to do.
And when you say it's enough to have certain features of the free field, I imagine the 3D Yang-Mills measure is not expected to be absolutely continuous with respect to the free field, for example.
No. So what we have is some kind of tail bounds. So if you take the random distribution and take its action on a smooth function, then we need exponential tail bounds for that kind of thing. So it's we have a list of conditions for that. So again, we don't know whether that will suffice. So then we probably have to take the conditions, but yeah.
And so, do I understand correctly? So you imagine having constructed the measure, and then it would be the initial condition for this flow.
Yes.
Okay.
Yes.
But then in the end, you'd like to go the other way around somehow, right? Could you explain a bit more how the second, I imagine that's where the second theorem somehow comes in. Is that right? Or
Yeah. So the second theorem will give you a state space for these Yang-Mills 3D Yang-Mills measures as the set of trajectories of the Yang-Mills heat flow. And then, you have a sequence of approximating measures, let's say lattice gauge theories, you have a sequence of approximations, and you would want to show that the trajectories that you get starting from these approximate measures, these random trajectories, they form a tight family on this state space, and then you have subsequential convergence. So that's, so that's basically what Balaban was also trying to do, get this kind of stability. So what Balaban was doing is you have this lattice and you have the lattice gauge theories, and then you have theories on coarser and coarser lattices, which are smoother theories. And if you go up to a certain level of coarseness, then you would want to show that the thing that you're starting out from, if you let it become finer and finer, but if at a fixed level of coarseness, you have a tight family. So that in probabilistic language, that's what you would.
So is it correct then that you're thinking of this Yang-Mills heat flow as an RG flow, a replacement for the RG flow?
Yeah.
So you imagine running it backwards in time somehow.
Yeah. And that's exactly how the physicists also think about it. These papers of Luscher and Narayan Neuberger that I mentioned. So they also think of it. And Luscher, in fact, has various computations that you would do with the RG flow. So these perturbative calculations using this flow.
But somehow this flow acts pathwise rather than, so the RG flow acts on measures usually, right? Measures of field configurations. What you're describing is somehow a pathwise replacement.
And then it you can transport it to flow on measures, because then you can say I pick a random initial condition from a measure, and then I look at its distribution after letting it flow for a while, and that translates to a flow on measures.
So would there be an analog in, sorry, I don't mean to interrupt with so many questions at this point. Maybe I should. Would there be an analog in a simpler context, say a field theory, say a 5-4 theory in 3 dimensions, where you could imagine doing something similar, right? You could.
So then you just have some kind of block spin renormalization that.
So your analog of the Yang-Mills flow there would just be like a nonlinear heat flow associated to the phi. Like a phi.
The gradient flow for the action, whatever the action is.
Okay.
So so let me tell you a little bit about the proof. So the main idea in the proof is that the randomness of the initial data helps ensure the existence of a solution, which may not hold for deterministic data of initial data of comparable roughness. And this general idea, as far as we know, originates in the work of Bourgain from the 90s to analyze a nonlinear Schrodinger equation with Gaussian free field initial data. And so a similar idea was pursued by Da Prato and De Bush in the stochastic PDE setting. And there's by now a large body of work building on this idea in many different settings. But as far as we can tell, for the Yang-Mills heat flow, there isn't anything like that. This is the first time that it has been done for the Yang-Mills heat flow. So let me give a very quick. So there are lots of technical things. I'll just brush aside all that and let me just present the main heart of the thing. So let's write the ZDDS equation as follows. Del T AI is the Laplacian AI plus a nonlinear part, where this is nonlinear part, because nonlinear part involves some commutators and some first order derivatives. And given initial data, this is equivalent to an integral equation. AIT is e to the t Laplacian times A0, I times integral 0 to t e to the t minus s the Laplacian times xi of AS ds. Okay, so you can write it in this form. And so then again, you can easily see that this is can be written as a fixed point equation, A equals WA, where WA is defined as follows. So you have a fixed initial data, A0. So WA of t is e to the t delta of A0 times integral 0 to t e to the t minus s delta Laplacian of xi of AS ds. So of course, the idea, as in most PD problems, is to apply a contraction mapping argument. And for that, we need to do what? We need to find a set of connections which is closed under a norm topology and is mapped into itself by W. That's the first thing. And to show that W is a contraction mapping on this set. That's the general contraction mapping argument. And finally, we need to show that the steps can be executed when the components of A0, the initial data, are massless free fields, or have some features of the massless free field. Okay. So fixed point equations can be set up in many different ways. And in fact, this is how proofs of the existence of solutions to the Yang-Mills equation and ZDD equation, almost any equation in PD is carried out. But the techniques of these prior works do not allow distributional initial data, as I mentioned. So we need to set up the fixed point equation in a different way. So the way that it has been set up historically doesn't allow distributional initial data. So that's the main challenge to set up the fixed point equation so that we can have, let's say, random distributional initial data. Okay. So for a C1 connection A, let AC0 be the maximum of the supreme norms of the components of A. So you can think of this as a supreme norm of A. And let AC1 be the maximum of the supreme norms of the components of A and all their first order derivatives. So these are very crude norms. These are not like HP norms, okay? But somehow we are able to work with these. So let's just say AC0 and C1 be the supremum norms of the function and the function and its derivatives, first order derivatives. Now suppose we have a continuous flow on the space of C1 connections between time 0 and t, where we are excluding the time 0. T is strictly positive and less than or equal to capital T. Given some gamma, which may be 0 or a non-negative or a positive number, gamma bigger than or equal to 0, define this new norm as a supremum over all t in this half-open interval of t to the gamma times the C0 norm of AT, and this plus a supremum of t to the half plus gamma times the C1 norm of AT, and take the suprema. So it turns out that this norm is complete on the space of continuous flows of C1 connections in this half-open interval and defines a Banach space. Okay. So this is actually a norm that defines a Banach space. And the time 0 is intentionally left out to allow for the possibility that AT approaches distribution as t goes to 0. So we are allowing that. And note that since gamma is non-negative, so suppose gamma is strictly positive, then both of these coefficients are going to 0. So even if AT is blowing up, these things may remain finite. And indeed, the finiteness of the norm means that the C0 norm of AT blows up at most like t to the minus gamma, and the C1 norm blows up at most like t to the minus half minus gamma as t goes down to 0. So this is what we are trying to control. Okay, so we have this QT norm. Now, given initial data A0, let BT be the solution of the ordinary heat equation with initial data A0. So this is the thing that we know how to control and analyze and do everything with. So we need to have everything in terms of the ordinary heat flow. Okay, so here A0 may be a distribution as long as this BT is in C1 for every T positive, which is a large class of distributions have this property. And then you define a ball. So you take this B, you fix this B, which is the solution of this ordinary heat equation with initial data A0, and let BTR be the set of all connections or all flows so that this QT norm is bounded by R. So the QT distance from BT is bounded by R. So you have something that's close to the heat flow. It may not be equal, but close to the ordinary heat flow. So then there is a lengthy calculation which shows that if for some gamma 1 in the interval 0.5 with a half open here, and gamma 2 in 0 to 1/4 such that the sum is less than a half, we have that the ordinary heat flow solution, the BT, has Q1 gamma 1 norm less than R, and it's close enough to being a fixed point. So WBT minus BT Q gamma 2 norm is less than R. Okay, if these two conditions are satisfied, so note that these two conditions are just conditions on the solution of the ordinary heat flow. Then you can show that W is a contraction mapping on BT gamma 2 3R for sufficiently small t, depending on R gamma 1 and gamma 2. So as soon as here this is 1, so this is up to time 1. And so then if this holds for some gamma 1 and gamma 2 satisfying these conditions, then we can show that this W that we get is a contraction mapping on a sufficiently small t and 3R. Okay. So this takes many pages, but we end up showing this. Okay. And the reason it's technically complicated is because this W, remember, is a nonlinear thing, and this BT is this solution of the heat equation. So if you apply this to the solution of the heat equation, then then you have to show that if you have some A in here and you apply W to that, so you're again applying the nonlinear thing, and then it maps into this. So there are things to show. Sure. So thus it will have a fixed point, which is the solution of your equation. Okay, so the whole condition is in terms of the solution of the ordinary heat flow starting with your given initial data. Okay. So now, how does this help? Okay, so any fixed point W is a solution of the ZDD equation with this initial data. So let's summarize what we have shown so far. So let A0 be our initial data, which may be a distributional connection. Let B be the solution of the ordinary heat equation with this initial data. Let C be the distance of B from being a fixed point. So it's WBT minus BT, where W is the map whose fixed points are solutions of our equation of interest. And suppose for some gamma 1 and gamma 2, where gamma 1 is less than a half and gamma 2 is less than 1/4, such that the sum is less than half, we have as t goes to 0, the C0 norm of BT goes like at most like t to the minus gamma 1. The C1 norm goes at most like t to the minus half minus gamma 1, and same for the C. Well, if you take the CT, the C0 norm of CT goes like t to the minus gamma 2, and the C1 norm of CT goes like t to the minus half minus gamma 2. Suppose you have these conditions, then the ZDD equation is a short time solution with this initial data. Okay, so this is what we have to show for initial data, which is the free field. Okay. So now, any questions until here?
So the short time, I assume it depends on the size of the initial data, is that right?
Yeah. So as I said here, on R, gamma 1 and gamma 2. Yeah.
So if you wanted to substitute in a free field, then you get a random short time. Is that right? Or
yeah, you get a random short time.
Okay.
Yeah, you get a random short time. Yeah. So it depends not exactly on the size of the initial data. It depends on this R, which is the size of the flow, that the ordinary heat flow that you get from the initial data. So that's more what it depends on. So this whole thing that I showed is valid in any dimension. So this is not for a 3D torus. So it's any dimensional torus. We are working on the torus for simplicity, but it's valid in any dimension. So now suppose our initial data is a random distribution. So it's not hard to see that for any x on the torus, if you take BT of x, where BT is a solution of the ordinary heat equation, it's a linear form in the Fourier coefficients of A0, and CT of x, which is a W applied to BT, okay? So the nonlinear thing applied to BT is a cubic form in the Fourier coefficients of A0. And so we can hope to obtain upper bounds on C0 and C1 norms. So for each x, this is true, but then you have to take the supremum over all x. So we can hope to do that using chaining arguments of Fermi, Talleyrand, Dudley, this whole world of chaining arguments. And so let's specialize to the case where A0 is d-dimensional massless free field on the space of G connections. So chaining arguments, using chaining arguments, you can show that the 4 conditions listed in the previous slide are satisfied for whenever gamma 1 is bigger than d minus 2 over 4 and gamma 2 is bigger than d minus 3 over 2. Okay, but we also need these. We also need gamma 1 to be less than a half, gamma 2 to be less than 1/4, and the sum to be less than a half. So you can see that these 2 conditions can be satisfied if d is 3. You can choose gamma 1 and gamma 2 so that these 3 conditions satisfy for d equals 3, but not for d equals 4. So that's why this thing works in 3 dimensions, but not in 4 dimensions. Okay. So this is to summarize, this is the idea that you start with this free field, then you express this BT and CT as linear and cubic forms in the Fourier coefficients, and then you apply this chaining arguments to take supreme over all x, and you control the supremum, the expected supremum norm, Okay, and then you apply the properties of these Fourier coefficients are for the free field, they are independent Gaussians with certain variances, but then you can relax those conditions and you can get things that are similar to free fields, and then you apply these chaining arguments to get this. Okay, so there is another interesting thing. So this is still work in progress. We are currently working on the case d equals 4 minus epsilon. So represent in terms of the decay of the Fourier coefficients. So this requires a more sophisticated fixed point argument, which increases in complexity as epsilon goes to 0. And in particular, number of conditions required for ensuring the W is a contraction. So I showed that you need these 4 conditions to hold. And for dimension 4 minus epsilon, as epsilon becomes smaller and smaller, you need more and more conditions. Okay, so the fixed point thing becomes more and more complex. And you can do that. Okay, so the fixed point argument that I said will work for dimension 3, maybe a little more than dimension 3, but not approaching 4 minus epsilon. So we can have that. Okay, so last slide I will say. So having shown that the short time solutions exist, the next step is to generalize the result initial that is similar to a free field. And we have a generalization of that sort, which only needs exponential tail bounds for linear and quadratic forms of the initial data. So we do not need really cubic forms, although you saw a cubic form appearing. Linear and quadratic forms are okay. And some features of 2-point and 4-point correlations. The space of distributional gauge orbits is constructed following an idea of Charalambous and Gross as a space of trajectories of the Yang-Mills seed flow on the quotient space, leaving out time 0 to allow for distributional initial conditions. And a criterion for tightness of probability measures in the space is proved using Uhlenbeck compactness, which is a very short. So this one line, it takes us, maybe 50 pages or something. So then we have this criterion. And what's left to do is that the results present here complete about half of the program initiated by Charalambous and Gross. The main thing that's remaining is to show that a sequence of approximations of a 3D non-abelian Yang-Mills series, such as a sequence of lattice gauge theories, does indeed behave like a free field, so that this whole thing can fit into that. And this would require proving correlation decay estimates for these approximate theories, and some estimates already exist. And hopefully, so this is again work that we are planning to do. Okay, so thank you. That's all.
So you expect the conditions to be the conditions you need, you expect them to be true, I imagine.
Yeah. So there are there are reasons for that. So in 3D, you have this coupling parameter beta, which I showed in the beginning. So that needs to be so if you take lattice gauge theories, that needs to be taken to infinity as the lattice spacing gets finer. And when it's taken to infinity and you fix a gauge, you do a gauge fixing. So on the lattice, if any spanning tree of the torus, discrete torus, will allow or a discrete box will allow a gauge fixing. And if you can fix a spanning tree so that it has, in most places, neighboring points are connected by short distances, short paths, then you have that most of the group elements on the edges that you get on the lattice gauge theory, they become close to identity. So you can do Lie algebra expansion, and locally, at least, it should behave like a free field. And then, the challenge is to somehow show these global estimates that we need, using that. So again, we I can't say we know how at this point how to do that, but we are hopeful.
So if I can ask a question, can you comment on what kind of observables you can expect to construct with this? In particular, Wilson loops are usually, non-local objects. What can you do with
so the kind of observables is with the regularized theories, you can have Wilson loop observables. You can also do this local curvature forms. You can, so once you have a regularized theory, local curvature forms are well defined, so you can possibly define those. And yeah, so these are the two things that come to mind right now, and there may be other things that we'll be able to construct. But the thing is, once you regularize, it becomes a smooth object, so you can do a lot of things with that. So as soon as you regularize, I mean, if indeed the Yang-Mills theories are like massless free fields, they have that kind of behavior, then you'd expect that the Yang-Mills heat flow will instantly make it a smooth field.
But if you wanted to check, let's say, area law for Wilson loops, you would first have to take an infinite volume limit, right? Do I see that right?
Yeah, yeah. No, so that's a different challenge. So yeah.
You said that in the first moment you said that you cannot go to 4 dimensions because these conditions which you had on the coefficients gamma 1 and gamma 2 are no more satisfied in dimension 4. And as far as I could see, maybe I did not see it correctly. If you go to 4 minus epsilon, it also does not hold, or
yeah, it also does not hold. But that's what I said, that for 4 minus epsilon dimension, you need a more sophisticated fixed point argument. So the fixed point argument that I showed is not going to work. So depending on epsilon, you'll need a fixed point argument depending on epsilon. As epsilon gets smaller and smaller, you would need a more elaborate thing. So the number of conditions that you need to define the fixed point argument will increase as epsilon tends to 0.
And does one see somehow that this increase in the number of conditions is related to the fact that in perturbation theory you need more and more counter terms?
It must be, it must be, and it's exactly how it's breaking down. And we exactly, we cannot reach dimension 4. So we can reach arbitrarily close, but we cannot reach dimension 4, and you need more and more things. And so it must be related in some way, but I don't exactly know how it's related.
Thank you.
Yeah.
I think that in the approach by Heirer and these guys, there is something similar where you have to kind of extract perturbation theory. So you have to extract something explicit, which kind of looks like trees, and then you can set up a fixed point argument. Is it something similar that happens in this 4 minus epsilon?
So again, as I said, there must be something similar going on, although the work of Heirer et al. Is for 2D Yang-Mills, the work that's available. The 3D work I think is not yet on archive.
I wasn't talking about their specific work on Yang-Mills, but the kind of the general technology of regularity to solve single SPDEs. Because there is a paper where they forgot, I think, with some fractional noise, which mimics 4 minus epsilon, where they have a systematic way of extracting, going all the way to epsilon as small as you want, but non-zero kind of thing.
I see. No, I don't know how those are related. So, yeah. So, I'm not sure. Maybe there is some relation.
Going back to this question I heard earlier, if you go to say 543 or even 542, where we know very well how to construct these measures, can one test this approach there? I mean, to basically carry out the program that you'd like to do, but in this much simpler setting where everything is understood?
That's a very good idea. One can certainly try.
Because it's different what you're proposing. This flow is different from the RG flow, etc. But there we know how to construct it in any way, and might be a useful test.
The gradient flow is always an option. I think the gradient flow is always an option. And there are other things where I think these continuum limits have not been constructed. So, for example, if you consider 2-dimensional these ON models. I don't think, and one can similarly consider these gradient flows for the ON model. So whenever you have an action, you can define a gradient flow, and then you can look at how it smooths, and so this is I think is always an option, and not very much has been done. So
Well, suggestion for 543 would be much more regular. ON models are not even renormalizable in 3 dimensions. I mean, so, and they're not formally renormalizable. They exist. We believe they exist, but they're not renormalizable perturbatively. But one thing I don't quite understand is in 3 dimensions, you explained that the Wilson loop is going to be singular, and so ultimately you have to do some kind of. Is there a well-known? I mean, there must be a well-known renormalization procedure perturbatively that makes these things well-defined, right? I mean,
yeah. So the idea would be to just regularize the connection itself and then take the Wilson loop observable. So that's how you can get a regularized Wilson loop observable.
But I mean, you know what the counter terms are? I mean, to make them well-defined, or do you have counter terms?
So right now, we are not, we don't have a Yang-Mills measure. So what we are assuming is that the Yang-Mills measure has been constructed and it has features of the free field. And then we are showing that this regularization, this makes sense,
And is it clear that it does have the free field? I mean, you can check these things usually perturbatively without, checking it rigorously. But is it clear that the singularities are free field like? I mean, or could they be singular? I mean, of course, we know that in 2 dimensions, 3 dimensions, they're singular, right, with respect to free field.
Yeah. So Lucier has done the perturbative calculation in his paper that I cited. So Lucier has a calculation which shows that roughly speaking, it shows that this works. So he he computes perturbatively. So the coupling parameter G going to 0. In that case, he has a series expansion, and he can write down the corresponding thing as as you take this flow, and so he's looking at 2-point correlation. So I think he's looking at the correlation between the curvature form at a point and another point, and then you can write down that expression, and you can write down the whole expansion, and then these perturbative calculations somehow seem to go through. That's as far as I know, and he claims that it seems to go through, and then you can have so in dimension 4 minus epsilon, he writes down the usual these counter terms, and writes down G in this renormalization way. And
if I remember correctly, Balaban has to calculate he's trying to calculate the partition function to some order, and he has to go to I think he has to go to 6th order to get something that he can control. So I don't know whether you see that kind of thing either, but
yeah, so that kind of thing will probably come up when we are trying to actually handle the Yang-Mills theories and show that the lattice theories, and show that, or whatever approximation we take, and show that it fits into our framework.
Well, again, let me just ask one more question. So do you need to control this thing for longer times, or is that not necessary?
It's not really necessary. So doing short times is fine, because there are existing global existence results, which are quite non-trivial, the global existence results. And but as soon as you have a smooth connection after a short time, then you have the global existence results.
So you do have global existence. I didn't quite understand that point. I mean, so for short time, then you show it's regular. Then does that guarantee global existence for you?
Yes. So it guarantees global existence, because there is this general result of Rada that on the 3-dimensional torus, for starting from any smooth connection, actually from any H1 connection, you have a unique global Yang-Mills heat flow. Yeah.
Right. If I remember, you mentioned that the Yang-Mills measure was not known in 4D, even for torus. But if I remember correctly, the paper by Magna, Ivaso, and Sineo, I think they look at the gauged fixed formulation, and I think they construct correlations of the connection. So isn't it like basically constructing the moments of this measure, whatever that is?
So we didn't quite understand what was going on. So maybe there is a measure, but we couldn't quite figure out whether a measure was.
I don't think they would like really construct the measures, a measure on some measurable space, but I thought they constructed at least what would be the moments of this measure. We had it.
Yeah, we'll keep trying to understand.
So maybe if I may ask another sort of general question. I mean, if when in the usual field theory approach in the continuum, there is always the issue of gauge fixing. You don't seem to have this issue at all with the Yang-Mills flow that you're constructing. But yeah, could you introduce it and regard, so to speak, a constraint flow in a certain gauge fixing?
So the ZDDS flow itself is like a constrained flow in some sense. So it's the Yang-Mills heat flow. So how it's obtained is that you take the Yang-Mills heat flow, the Yang-Mills action, and then you do plus lambda times a gauge fixing term. So you do a gauge fixing, and then you take the gradient flow of that. And that's how the ZDDS flow is obtained. So in some sense, the gauge fixing is hidden in that. And that's why it becomes a much nicer, nicer flow.
And so is there any issue about Gribov copies or something like this in that approach, in this differential equation?
Not that I know of. Not that I know of, because at least starting with smooth connections, you do have global solutions, and yeah, so.
Thank you.
I suppose there are no further questions anyone has, or yes, we've had a lot of questions already. So in that case, well, thank you, Sourav, again. It was a very nice talk.
Thank you. So nice to see all of you.
Thank you.
Thanks a lot. Goodbye.